Yeah. Do they have like fading models?
Roy's here.
Roy's here? Okay.
All right.
So there's no way out from now on.
That'll be the next thing after.
We have several different channel models, and I mean, different
Yeah.
ones that have small scale, large scale.
Hi, Ali.
Hi, how are you?
Happy New Year.
Happy New Year to you too, thank you.
It's not mine.
Life got more interesting.
Hi Marco.
Hey. Ali, don't forget to unmute the,
Yeah, mute.
well, unmute it, so
Unmute,
we can
yeah.
actually hear
Sure.
the presentation.
Yeah, I guess we should wait for Roy too.
I think Roy is here.
Happy New Year, Marco.
Yeah. Happy New Year.
You guys all have snacks?
Oh,
Alright, give me a second.
Sure.
Is John on the line?
Yes, he is. Hi John. So we are going to start in probably a minute. Marco is here too.
Hi, John.
Hey, Marco.
Happy New Year.
Yeah, Happy New Year to you too. Thanks.
Thanks. Actually, if you have 5 minutes afterwards, I'd like to chat with you a little bit.
Okay.
No, alright, I'll see. Save this one for someone with. Oh, I guess John Kenny is in the machine somewhere.
Yes, on the phone. Yes,
Hello.
we're all here now. I guess as a reminder, it's fine to ask questions during the presentation. We will have a session for all to ask questions, and then John, there will also be a closed session with another opportunity to ask questions where only Ali is in the room. And then after that we close. But, yeah, welcome everybody to Ali's defense. Ali has become our resident vehicle communications expert here over the years. With that, please take it away.
All right, thank you, Marco. Yeah, let's start. So, hello everyone. My name is Ali, as you know, and today I'm going to talk about my thesis, context-aware congestion control, pedestrian safety communication. This thesis has been done under Professor Grutisser supervision, and committee members are Dr. John Kenny from Toyota North America. He's on the line with us. Professor Richard Martin and Professor Roy Yates. So let's start with some statistics by NHTSA, National Highway Traffic Safety Administration. So every year NHTSA is releasing some statistics about fatalities on the roads, and the latest one is 2016 that is out there. Maybe 2017 is recently out there, but in 2016, as you can see, almost 6,000 pedestrians were killed on the roads, which shows 9% of increase, which is not a good news, and the highest since 1990. And well, vehicle occupants as well, so there is a lot to do in this area, and I am going to take a look at some of the options that are out there available in vehicles, and you know, we will make our own way to the topic of this thesis. One option is the standalone sensor-based systems. As you can see, we have LiDAR, radar, and camera-based detection. The one major drawback of all these systems is the limitation that they have. They all need line of sight to work. And as opposed to this, there is also some communication-based systems. We have DSRC available, dedicated short-range communication. It's a Wi-Fi based system which enables two entities on the road to communicate with each other. It could be vehicle-to-vehicle talking or pedestrian-to-vehicle talking. And as you can see, this demo has been done by West Virginia University and Hyundai. We have a pedestrian here behind the car, and as this car is approaching that pedestrian, the driver is getting a warning here. So this just is a demo that these systems work. You know, they have some requirements, but they can work. This is the demo. But the question that we want to take a look at today is, are these actually 4 questions? What if we have so many people around? If they are all carrying, like, you know, they are all carrying a smartphone in their pockets or in their hands, and their phones is DSRC enabled, transmitting these messages, safety messages to cars and traffic lights and everything, and we have many of them. How does a 10 megahertz narrowband wireless channel is accommodating all that load? So that's the first question. What if we have too many pedestrians around? Next question is, does every pedestrian need equal share of the channel? And with that, we mean, just consider the case that I just showed you. We have a pedestrian which is in danger, we call it at risk. And we have many other pedestrians, we can have many other pedestrians on the sidewalk, and they are safe relatively, right? So maybe they don't want to share too many messages with the car and making the driver aware of this situation. And one clarification I should make. In these thesis, in this system, we are talking only about the pedestrian transmission from the pedestrian perspective, meaning that we don't care how cars are handling these messages. So they can use it as they wish. They can develop apps to get warnings, smash the brake, or many other things. But we are only seeing this as the perspective of the pedestrians. So getting back to the questions that we want to answer, does every pedestrian need equal share of the channel? Meaning that their situation is different, probably they should get different share of the channel. Third question would be a weighted fairness, meaning that, well, we should look for the clues, for the context clues, to categorize probably these two if the answer to these questions are yes, which you can guess that it is yes. How we should actually extract some clues from the context to make these categorizations. And at last, we are looking into if that is not sufficient in terms of the channel load, and we are not doing well still, what should we do in terms of controlling the congestion on the channel? So one tool to do this is having a simulator and having a good confidence in that simulator. And as we are looking into options and looking for answers, we can have that simulator to help us evaluating the system algorithms that we are developing. So let's start with the simulator designed for a pedestrian to everything, P2X, pedestrian to everything communication. Apart from calibrating a simulator for DSRC, which goes to the different parts, like different modules. We are going to talk about it later, but let me give you a hint. Apart from the fact that we need the receive models to be aligned with the DSRC radios that are off the shelf available or prototypes, we are also interested to have a concrete analysis of a very solid analysis of what happens on the road and what to focus for having a scenario that we can use through the entire thesis to whenever we want to evaluate something, we can use that scenario. So starting with this document, it was at the time a draft of a standard for pedestrian communication using DSRC. It is indicated that in that document that 67% of the crashes on the roads are one of these two categories. Not necessarily with buildings and non-line of sight, but it's either one pedestrian is passing crossing the street, either in this direction, or it's a left turn, right? Or it's moving along or against the traffic. So with that being said, we looked into a scenario in the neighborhood of Times Square in Manhattan, extracted the map, and based on some documents from New York City government, it shows that it's at the center of the heat map of pedestrian fatality. And we wanted to focus on that for several reasons. One is it's a crowded city plaza, and if we want to study the congestion of the channel, of the wireless channel that pedestrians are going to use, it's better to focus on such area. Second of all, it's very challenging because we have poor positioning accuracy, and that poor positioning accuracy is going to contribute a bit to the design of the algorithms that we are going to talk about. Moving from that, what we did like 3 years ago, 4 years ago or 3 years ago, I went out there, just took the camera from Ivan. I got the camera from Ivan. I went there and stood somewhere and took a lot of pictures from different phases of a traffic light, pedestrian traffic light at different intersections. So with that, I was able to get the cycle of the traffic lights at some of the intersections in the map that I just showed you. Counted number of people waiting for green light, and then when they were like passing the next cycle, and I had a rough number about what is the pedestrian traffic on that particular intersection.
So when you say you get the cycle of the lights, what does that mean?
Meaning that when it's red, at maximum how many pedestrians are waiting there, waiting for the green light, then it passes, right? They all cross the street, next cycle, how many again? And then having a number, like, you know, having an estimation about the amount of traffic, pedestrian traffic in that intersection. And I did it for a few of those intersections of the map that I just showed you. Let me show you again. A few of these intersections, and I had an idea about how many people are crossing those roads. And why did I do that? Because that's one of the indicators that we can get a scenario which mobility scenario of the map that people are walking around on that map in the simulator, right? And we can say how close is that to reality by focusing on those zones that I did this counting on, right? And comparing it to the mobility scenario that we generated with the simulator. That's what I did. And we got an acceptable, you know, scenario to start with. And that is something that I use through this whole thesis for evaluating algorithms and using it in the simulator. Another thing that I want to talk about the simulator design is the propagation environment. So we decided, based on the very dense building structure of Manhattan, we decided to have 3 types of links. One is, we can say no building shadowing. I call that name, I use that name instead of line of sight because you can still get like a lot of obstruction between the transceivers. But it's not gonna be a building. A building is not gonna be on the way of the transmitter and receiver. Another form is building shadowing, which means that they are on the different roads, but they are sharing an intersection. And the other type is building block, meaning that it's completely blocked. Given the size and the material used in New York City, signal is not going to the other side. And we are assigning actually in the simulator different propagation models to these categories. What simulator does is based on the building structure that it has from the map, it decides which kind of these links the communication is for each packet transmission, right? And then it looks for the corresponding propagation channel model and calculates the receive and interference power, signal power at the receiver. Just one heads up, I use a preliminary propagation model set for all of these for the next 2 chapters, meaning the ideal positioning system when we go through the results is gonna be with a model developed by some paper that I'm going to tell you about more. And finally, we were able to get a model for ourselves, calibrated using the data that we had from connected vehicle system communication data set available by CAMP. And in the last section, we have 2 sets of results trying to understand the impact of different propagation models and the accuracy of propagation model on the evaluation of the algorithms that we have. Let's start with the modeling propagation. This was a line of work in parallel with the algorithms that we developed for the thesis. It's slightly different, meaning that we used a data set to calibrate propagation models for the environment that we have those simulations in. Well, I talked about most of these. Like, if we have like a large scale performance evaluation for a large scale system, then it is not very wise to go with testbed. We can't do that. We can't have like thousands of phones. Then one solution would be to use simulators, right? And for doing that, we need a really calibrated models to have confidence in the simulations. That's why we go with, in this part of the presentation, I will walk you through the steps that we took to model the propagation for intersection environment specifically and calibrate it using the data available. Part of the CAMP project, Crash Avoidance Metric Partners, we had done a few field experiments with the DSRC radios. One free space environment, meaning that it was in a test track without the cars, just the radios at the proper height. We collected a lot of data. We moved to public roadway with dense vehicular traffic. We did the section of a freeway, 16-lane freeway in California, and then we did, I'll show you in the next slide, an intersection in that environment, plus one controlled emulation of vehicular traffic in test track with 4D cars. This is the intersection. This is what we focus on in this thesis. It's an intersection in Orange County, California, with a lot of lanes. We chose it because we had a lot of traffic there, and we used 10 test cars driving in different patterns, predefined patterns, and we collected data to understand how these DSRC in that band is actually behaving in terms of like communication, signal strengths, and everything. It's not perfect because we are talking about phones, smartphones communicating with radios in the cars. So one party is the smartphones, and we have slightly different things happening for them. In an ideal world, we should have been able to do that, but this is the data set available to us, and we worked with that. First step, to model the propagation, we try to break the data set to subcategories showing different behavior. For example, longitudinal, meaning same road communication. Each dot in this plot is showing a received signal strength for a given transmitter-receiver range. The left plot is showing all the communication for same road, meaning that the transceivers are located on the same road. And around the corner is when each of them is on one road which is intersecting. They are having a building in between somehow. As you can see, the behavior is way different. So I'm gonna show you that we can't even go with the TX-RX range only to model this behavior. What we did was to use a log distance model for the longitudinal cases. So we are able to capture the path loss with a log distance model, plus shadow fading and fast fading. And for the around the corner cases, when they are like on different roads, we are using 3 different distances. TX-RX distance, the range between the transmitter and the center of the intersection, and the range between the receiver and the center of intersection. And we are calibrating these models. I'm going to show you in the next
Can you
slide.
explain that lower model? So
This
Yeah,
model?
it-
Right,
looks
so
like you have
I
three-
different.
you have 3 pieces or something, right? So
Exactly, yes.
Okay.
Actually 4.
oh,
Right? So this is one of the observations that we had. We plot this RSS samples. This is color coded, right? We plotted for the distance between the transmitter and the center of intersection, the distance from the distance of the receiver from the center of intersection, and we saw that this is more relative than this, the right figure, right? So we decided to encode all these available data that we have to see how well the model is behaving, how well the model is capturing these effects, and it was successful. Yeah, and then moving forward with shadow fading and fast fading components, we use autoregressive process to capture the remaining oscillations of the received signal power, and whatever remains is a Nakagami model. It can be captured with a Nakagami model. These are the fast fading things happening because the wavelength in 5.9 gigahertz communication is very short. That is one reason that the slightest change in the environment can make a big difference. So we are capturing that with fast fading, and when we are calculating the main loss component, this is how we decide how much of it goes to these variations as shadow fading and how much of it goes to the Nakagami model as those jumps like between each sample. Moving forward, giving it to the the calibration procedure, the outcome is a lot of coefficients that we get for the different parameters of the models that I just told you. And again, we are breaking it one more step. How? We are looking into the data set as for per corner in that intersection, reference intersection that we had. Meaning that we capture all the data that belongs to northeast, for example, northeast corner, and calibrate the model for that and get these parameters, right? And we do it for all of them at once too. So it's like different level of resolution, I would call it. Meaning that we are feeding the model for each corner specifically. We just want to take a look at it, right? And then we combine all of these data for all of the corners and then feed the model again. Depends on what we want to do. Given that we want to use this calibrated model for our map, the map that I showed you, we are not going with the specific corner parameter fits. We go with all the data sets and calibrating the model for all the data sets that we have. We are not making the resolution for each corner specifically. We define this metric to calculate the accuracy of the model. How it works is, the first row, you are seeing the PR for the distance between transmitter and center of intersection, receiver to the center of intersection. this is what we logged, and we calculated from the log files, right, for each specific corners. And second row, you are seeing the simulation results using these fitted parameters. As you can see, we are able to capture the differences between different corners, and the simulation results is following whatever that is happening in reality. This is mostly caused by the different building structures at different corners. So we have, for example, a very huge building at northeast and at that intersection that we collected data from, but the building that we have in southeast is probably smaller and more close to the edge of the road. So if you take a close look at the map, you will understand what I'm saying. Maybe I'll go back at some
Do
point.
you have
to
a
show.
picture of the geometry that you're?
I'm not sure if this is showing it, but yeah, here. This is northeast, we have a building here. The southeast, we have these huge spaces here, right? Southwest, actually. And then the building, southeast, the building is right at the edge of the sidewalk.
And the measurements that are recorded are pedestrians on the sidewalk in front of the building?
Actually, there are radios deployed on the cars, and cars are moving between, all of these lanes here. So that's
And
that's the
where
data set.
So
That's,
those are, where are the receivers for those cars? Or like, those cars are getting RSS, you're either recording the RSS from those cars
Exactly.
somewhere.
Mhm.
So where are the receivers that are making?
Receivers are cars. So cars are transmitting and receiving at the same time. All of the 10 cars. So at any moment they are transmitting packets and logging it, as well as receiving from all other 9 cars and logging it.
So when you talk about the parameters for the southeast corner, say,
These?
like, yeah.
Mhm.
So, okay, so what is it, is it a radio that's on the southeast corner?
Oh,
Is
no,
that what-
actually, let
what,
me tell you. So here, we call this southeast corner, right?
Yeah.
This car is transmitting, this car is receiving, right?
Ah, I
And we
see.
know that there is a building between them. Then
Okay.
all the communication that happened in these in these one corner, we are, grouping
So
them together.
southeast is describing the kind of the location of the obstruction in the radio channel.
Exactly, yes.
Okay.
Yeah.
So I guess I have another question on the way the cars were moving through the intersection. Is that picture meaningful, or they just
Which
make
one?
the
This?
corner, you had cars moving through the intersection?
Oh, they are moving all the time. So
Okay.
what we had
So
a
it's just
control
cars driving
station
through the
telling them when to
intersection.
move.
Yeah.
They had to follow traffic rules.
Yeah.
But we had these opportunity to coordinate them to meet at the intersection.
Okay, so you just had cars kind of going out of this intersection?
Exactly.
But
Yeah.
somehow each time you got a measurement, you knew what the positions were?
Yeah.
What
So we are logging GPS, heading, speed, the content of the message that they are transmitting to each other, the location of the car. I told you that. RSS for the received packets, successfully received packets, and a few other things, and the timestamp of the transmission and the reception. We have sequence number for the packets, so we are able to correlate all of that and calculate PR. We know what happens where, you know what I'm saying? So with all that, we were able to calibrate the models. And to measure PR, we used these equations, these set of equations, and what we do is to calculate a value for each tile. We compare these 2 tiles, the corresponding tiles, to each other, and measure the difference, sending it through these equation, and we get an accuracy. And then overall, we are going to, we actually average across all of the tiles.
So,
And we get
can you
these numbers.
explain what each tile is? So what's the X and the Y?
So,
What's the-
X means, so let's talk about one of the tiles here. For example, these tile, right? The first tile in the rightmost figure at the bottom, John. We are talking about just a tile. I just want to give you the idea of what they are representing. It means that whatever transmission happening between 20 meters when the TX, when the transmitter is 20 meters away from the center of intersection, 20 to 40, whatever transmission happens here, right? When the receiver is also 20 to 40 meters away from the intersection, then we are grouping them all together, counting number of transmission happened, counting how many of them were received in the receiver, right? And then we are able to calculate packet error ratio.
Right,
And
so
that's
the
a
Z-
number.
Right, so the z-axis is the packet error ratio.
Exactly, the color coding.
That's what it, yeah, like the height.
Yeah. And then that actually makes us able to enable us to calculate a single number for our model. We have two models from literature. We have a general model, meaning that the model fit that we got for the entire data set that we had, and we have corner specific fits, right? So with all these, we can see like the median of the accuracy, simulation accuracy, we can able to achieve like 80% of accuracy, which is a good number. And this is the model eventually I used as the most accurate propagation model for evaluating the last section. Moving from that, let me start talking about the pedestrian to everything communication. We started with this goal to be able to just evaluate the system under some relaxed assumptions. Meaning that we are saying no positioning error, the system has no positioning error. That's a very unlikely assumption, but we start from there. We want to, what would happen under such cases. So let me skip this part. No, actually, this is good. So what we did was we said, okay, every pedestrian in the simulations that we talked about is transmitting with 5 Hertz. We call it baseline, meaning that no intelligence is being used, no information is being used to adjust the transmission rate. They're always transmitting with 5 Hertz, meaning 5 packets per second to the cars, whenever they are outdoor. We are not considering people's smartphones in the buildings or whenever they are riding a car. Whenever they are walking, they are transmitting with 5 Hertz. We call it baseline. And then we create these 3 other variations, meaning that if we have an ideal positioning system with no error, we would have been able to say whenever pedestrians are moving, right? Whenever they are in a street, just transmit them and don't transmit other times. With having these variations, let me just walk you through what happens. So baseline meaning that everybody transmits like all the time, as you can see here. Moving pedestrian means only those are transmitting who are moving. Multiple rates, meaning that if the pedestrian is stationary, probably they don't need to send as frequent as the others. So they will transmit with different message rates. These are just the cases that we want to see how the channel is occupied. What is the channel load under these assumptions. And in a street meaning that whenever they are crossing the street, they are the only ones transmitting. These are the performance metrics, PR, packet error ratio. We use inter-packet gap. Well, you don't want these awareness messages to get like too far from each other and the cars don't know what happened to that pedestrian in between. So that is one metric. And channel busy percentage is another metric. This is probably the most important takeout from this part of the evaluation. We actually measured the channel busy percentage, meaning the amount of time that somebody was transmitting something and a channel is marked as busy in terms of like radio. If they are listening to the channel, they can say that it's busy, we can transmit. right? We calculate that number every 100 millisecond and average over 10 seconds of simulation for the map that I showed you and the, the mobility trace that we got. And these are the results, meaning that baseline, if they are transmitting all the time with 5 hertz, we don't have any chance. Even if they are sending with 1 hertz, it's very, very crowded and the channel is very congested. And if the channel is congested, you are losing a lot of packets. The receiver is not listening from the transmitter as frequent as it should be, like the cars are not being aware of the cars as frequent as they should be. So the honest street is showing a promising number. The thing is that we don't have an errorless positioning system. The assumption here is that we have zero error, no error for the positioning system. That's the problem, but it's good to know where we are standing. We should do something about this. And other metrics, just want to show you that, for example, packet error ratio when we are transmitting with 5 hertz, and if it's the baseline, it goes all the way to around 95% of packet loss for 135 meter distance between the transmitter and receiver. But again, let's throw back to the research question that we had. The first step was to recognize where we are standing. What should we do? And in terms of the channel load, we saw that, well, we need to do something about it. We need to develop algorithms to overcome this.
These channel busy percentages, are they not just kind of in proportion to the number of pedestrians wandering around?
They are, exactly. And the policy that we use to transmit messages. Policy means that, for example, this on a street pedestrian, meaning that the pedestrian, the smartphone will transmit whenever crossing the street, right? Otherwise, it doesn't transmit. And it can happen under a very hard assumptions, like, you have to know the exact high definition map of the intersection, you need to know the errorless positioning of the pedestrian. So we just wanted to know if it's possible to make it better, right? And we can make it better, but now we have the problem of the assumptions that we make, right?
Yeah. So what is the baseline in that?
Baseline is transmitting with these rates all the time, if they are in pedestrian transportation mode.
And there's some kind of a multi-access protocol, like it's DSRC or something?
DSRC, we use DSRC. So we have MAC layer, everything is working as they are expected, right?
Okay.
It's just a matter of the decision of when to send these safety messages. Baseline meaning that 5 hertz all the time if they are walking.
And somehow is there some literature that says 1 hertz is not good enough for pedestrians?
Yes, it's not good enough, really. But so the recommendation was 5 hertz originally, and it moved to 10 hertz. We are going to go with 10 hertz from this point on. But 10 hertz doesn't say, they don't say that they have to send 10 hertz. It says that that's the maximum rate they should go to. Beyond 10 hertz, there's not much gain. It's just battery consumption, right? But it makes sense to go sometimes to 10 hertz. Here it was 5 hertz. It was 2016. The draft was saying 5 hertz is recommended maximum message rate. That's why we went
kind
with
of
other
1 hertz
numbers.
is like 1 step, right? People walk about, they move their feet about, kind of.
Right, yes. So generally
one
it's not too
step
bad.
per second.
Generally, it's not too bad. But if you are considering the fact that these packets can be lost because of the packet collision,
Yeah.
so you might lose like 2 consecutive messages, right? So between 2 received messages to the driver, to the car that is approaching you, 3 seconds of gap.
So
And in that 3 seconds, many things can happen, right?
So these numbers are based on kind of your Times Square kind of
Map, exactly.
Pedestrian loading.
Exactly.
So
That's the mobility trace that we use from now on for every single simulation.
So in New Brunswick, maybe the 10 megahertz channel is fine.
Yeah, exactly. Yeah. So this is some sort of a stress test.
Yeah.
Look at that way. Yeah. Yep, moving from the fact that, okay, we need to do something about it, now we are thinking about heuristics that we can use to reduce unnecessary messages. What we call unnecessary is really depending on the context. Here the context is that if you are walking on a sidewalk, you less likely get hit by a car. If you do, it's definitely the car's fault. I mean, it's like, you know, going to the sidewalk. So you don't need to send as frequent as someone who is crossing a road. That's one simple context that you can use to decide with what message rate you should transmit. We want to take a look at that. The idea is like what I just told you. The ideal case is if you have a high definition map for the intersection, plus if you have a very accurate positioning system, you are able to do that. But we don't have that. So we saw actually tens of meters of error when you're walking in Manhattan. So apart from the fact that that could actually affect the usefulness of the packets that drivers are seeing, cars are receiving, it actually makes it hard for us to decide when to transmit with what rate. This is the part that we want to focus on. The part in the cars is not our problem. They should decide whatever they want to do with those messages. There are tons of applications that they don't need very accurate positioning. So we are not talking about that part. We are only talking about the part to how to use these context clues to reduce the message rate. That's the whole goal. Solution is if we mark the crossing points at the intersections, either manually, someone goes under, using an application saying that these are the points that pedestrians use to normally cross the road. We are not talking about random jaywalks, right? You can do that, or you can, if you have access to big data sets like Google Maps data sets and locations of pedestrians, you can crowdsource and find out which points they are normally crossing the streets. If we have those points, then we can define a guard zone around them, and whenever the pedestrian location falls into these guard zones, these circles around these intersections, they assume that maybe the pedestrian is intended to cross the street. Then they consider that pedestrian, we consider that pedestrian at risk, and shift that pedestrian to the maximum message rate possible. If they are not within those guard zones, then we assume that they are walking in blocks, right, on the sidewalk in blocks, and they are not crossing the street. That's the intuition here. Cons and pros. Well, no need for detailed map. We are just roughly saying that these regions, whenever they are falling to that region, they are probably crossing the street. The cons is actually one of the drawbacks is not all the pedestrians that we mark at risk are actually crossing the street. So we are transmitting more than enough. Sometimes we have too many false positives. Yeah, false positive. Which doesn't hurt to transmit more than enough. It's just not the best way to do it. The algorithm is defined this way. Well, it gets those crossing points. Sorry. It gets those crossing points, the latest GPS reading from the sensor, the estimated error from the API of the device, and the width of the maximum width of the streets around that pedestrian. What it does is, if the VRU is moving, VRU, vulnerable road user, the pedestrian, is moving, then it calculates this number, this threshold. This is basically the diameter, the diameter of the guard zone around those crossing points, right? It calculates that number based on the width, the maximum width of the street around the pedestrian. Why we do that? Because we don't want to stop marking the pedestrian as as at risk whenever it goes out of this guard zone, right? If we have a very wide street, then the pedestrian is crossing it in the middle of the street, it gets marked as safe. So we consider the width of the road as a parameter for calculating these thresholds. After doing that, if again it falls into the guard zone, it will be marked as at risk. There is a component of jaywalks. This algorithm is able to actually consider those cases as well. If none of these cases, then the vulnerable road user is temporarily marked as safe. And for the classifier performance, we are using recall and specificity. Well, recall or true positive ratio is how well the algorithm detects the at-risk pedestrians. Specificity, false negative ratio, is how well the algorithm detects the safe pedestrians. And after running the simulations, this is the results that we get. Just a heads up, Oracle solution is a solution where the best is being done, meaning that if the pedestrian is on the road, the simulator knows it. You have every information in the simulations, right? So we run simulations considering the fact that we know everything that is correct, that is right. We call it Oracle solution. This is the best that we can do. No surprise that we can do 100% for both specificity and recall, right? Then we are having like different guard zones and different thresholds, and just calculating these numbers. Apart from the fact for the classifier performance, what we are interested in is to know how well we are doing in terms of CBP again. This is the point, again, just a reminder, this is the point that we want to know is if this is sufficient to control the channel load and keep the performance as good as it can be. Let me skip this part and throw back to questions that we had.
Hi, Ali.
Yes?
Ali, this is Sky. You talked about CBP a couple of times, and you're showing it again here. Can you just say something about what is a desirable CBP? For example, is lower always better, or what is it we want to see for CBP?
I see. Yes, so for CBP, there is a threshold, meaning that if we are keeping the CBP at that point, that's the most desirable thing. Because beyond that, higher than that value, we are increasing the chance of packets getting collided on the air, and we lose both packets. And if we go below that number, below that threshold, we are actually, the channel is underutilized. We are not, we are not using the channel properly. So that number is, it has actually a few things that indicates that number, what that number should be, determines that number. One thing is the packet length. For the given packet length that we have for personal safety messages, the CBP number is around 70, 75 to 79. So if the CBP is around that number, that's the most desirable case. Did I answer your question?
Good.
Yeah.
Yeah, that answered. Thank you.
Sure. So, throwback, does weighted fairness resolve channel congestion, the context clue that we used? The answer is no. We still have a lot to do here. So, next step is how to further control the channel. And this is the congestion control algorithm. To the best of our knowledge, this is the one of the first works being done for pedestrian communication channel congestion control using the context clues, and it is able to consider different application requirements. We have different applications. Safety application usually needs more accuracy and more frequent message transmission, but another pedestrian might just use an application to communicate with the traffic light to let the traffic light know that I am going to cross the street, change the cycle, or whatever, right? So different message ratios creates this need to have a congestion control algorithm which is able to work with different application requirements. And that is what we did here with a realistic GPS error model. That's what we added here. So this is a system architecture. We have a multi-rate controller. This is the channel congestion controller that we talked about, and I'm going to walk you through it. And the assumption on the upper layer, application layer, is a heterogeneous application layer. It is time and location variant application requirement, meaning that application is seeing different positioning errors time to time. It's time variant requirement. If the positioning accuracy is different, the application layer might decide to disable some of the application. Like the safety application is not good enough. We have 20 meters of error. How could it be good to let the cars know about where I'm standing, right? But it is maybe good enough for the traffic cycle adjustments, right? So based on that intuition, the application layer might decide to disable some of the applications time to time. So it's time and location variant message rates requirements by application. So I just described these two bullet points, and plus the multi-rate controller, what is different is we need to do some energy efficiency designs here. It's not V2V communication, it's not a vehicle. It doesn't have access to unlimited power source. The battery limitations are here, and therefore we need to do something about it. And this is the goal. If two message rates, if two pedestrians, let's just consider the location variance part of it. If two pedestrians have two different message rate requirements, R1 and R2, right? Then if we have a congestion control out there, considering the load, the current load of the channel right now, and decides how much those message rates, requested messages should be reduced, it should be proportionally for R1 and R2, right? That is the one of the primary goals of this design. And well, it employs the collaborative channel assessment to save power, meaning that the radio doesn't need to stay up the whole time, the entire time, to listen to the channel to be able to measure the CVP. They can just use third-party nodes to measure the CVP and sending to a smartphone.
So what is this, the RPSM?
RPSM, meaning that that's the rate that PSMs are generated and transmitted with. So a smartphone gets a requirement from application. Application says that I would like to transmit 10 hertz, right? Meaning that 10 messages per second, right?
Yeah.
Then the controller listens to the channel, sees that the channel is very congested, right? It cannot afford like 10 messages per second. It calculates based on Limerick congestion control equation, right? It calculates a rate, we call it RPSM. Yes.
So wait, RPSM is the target set by the application, or is it that R1 is the target?
R1 is target.
You want them in proportion, but I'm just not sure
Right.
which is which.
R1 is the target.
Yeah.
RPSM is the calculated by the congestion
Okay.
control algorithm. All right, and
So,
this
so
is
you're asserting that's the goal. But in some way, like I think, somebody who wants 10 hertz being cut to 5, maybe that's fine, but somebody who says they want 1 being cut to a half might be much more terrible.
yes. So the thing is that I guess I have it here. Yes. So the thing is that this algorithm is able to do what you just mentioned, meaning that if somebody has some phone has requested 10 hertz and another phone requested 5 hertz, and the congestion control knows that the 10 hertz can go to 5 hertz, affording 5 hertz, right? The other congestion control is distributed. 2 congestion control algorithms are running, right? The other one is deciding 5 hertz should be reduced to 2.5 hertz, meaning that the amount of reduction, the reduced amount, should be proportional for these two.
Yeah.
And the thing is that what we want to do is to show that the system is stable. We don't have fluctuations in the system. We want to show that it works, right?
Yeah, but
First of all, getting an
What
algorithm.
I'm asking, the question is that an ad hoc choice on your part, or is there some literature, or is there something that says, oh, for kind of pedestrian safety, this proportional scaling is the right solution? Like
I see.
I'm putting forward the other
I see, I
idea
see, I
that,
see,
oh,
I see.
a 50% reduction of someone who asks for something small might be much more dangerous
I see.
than a 50% reduction of
Yes.
someone who asks for the maximum.
Let me answer that question this way. So instead of giving an ideal message rate, which is the target one, right? Applications are giving the controller two message rates, maximum or desired message rate and the minimum that they can be operating under it, right?
Oh,
If
is
they
that-
have, yes.
okay.
And the controller calculates a number saying that I can afford this. If it's below the minimum requested by the application, it will use the minimum.
Okay.
Actually, that's one of the design discussion of the algorithm, because at the end we are showing that even doing that, even so that the algorithm is prioritizing the minimum message rate requested over its calculated rate, the system is stable. Is stable. Yeah. Yep. So line 3 and 4 and 5. These are the steps that the Limerick congestion control algorithm uses to understand if the message rate should be reduced or increased, okay? And after that, this is just one step calculation that it actually calculates the RPSM, and based on whatever that the application at the time is requesting, the RPSM would be adjusted. And at the end, it will check with the boundaries of message rate requests, like R minimum and R maximum, and decides what should be RPSM. One advantage, this is another advantage over V2V congestion control algorithms.
Yali?
Yes?
Ali, this is John. Can I go back to that slide
Okay.
48? So I want to understand here what's going on. So you mentioned in the dissertation the weighted version of Limerick, where different nodes use different values of beta. But I think what you're saying is you're not actually using that here. Instead, everyone is using the same system-wide beta, and you're getting the proportionality from line 7 based on the ratio of the R maxes. Is that right?
That is right, actually. I don't remember the equation number, I'm not showing it here. Based on one of the equation in the dissertation, I am showing that the proportionality between betas is eventually translated into the proportionality of the requested message rates. And with that information, you're right, what we are doing is to directly using a R system, meaning that a system-wide maximum ratio, we are calculating RPSM, and then we use the maximum message rate requested by the application at the time to calculate the proportion to our system, and that is what gives us RPSM. So the difference between what you just said, using betas to calculate these numbers, and this way that we are doing it, is that we translated the proportions between different betas to what we finally want out of the system. What we finally want out of the system. What we want is the proportionality between RPSMs for different requested message rates.
So, can you comment then on how this version of the algorithm on 48 behaves differently than a weighted beta version?
Right. For the weighted beta version, when the congestion control is getting a new message rate request, let's say that the message rate request went from 1 to 2, right? It needs a few cycles to use the new beta to converge to the new calculated message rate, PSM rate by the controller. Just like Limerick does, right?
Right.
But here, with translating different proportions, proportions between the different betas to proportions between different RPSMs, what this algorithm is doing is just one-step calculation of the target PSM rate that should be used. Using the information that we know, different proportions between different betas is translated directly to the proportions of PSM rates. Am I confusing you?
So, no, I think I understood, and I think that that's a very important point, actually. So, you know, when you first started talking about using the weighted beta version, my concern was, well, that could take a while to converge when you have a new RMAX, and I think this version that you have is going to be much more responsive to changes in RMAX. So I think that's an important distinction. I just wanted to hear you talk about it a little bit.
Thank you, John. Actually, I'm showing it here. So as you can see, pedestrian B, I'm talking about the right figure, the top part. The requested maximum rate for pedestrian B is falling at sometime t plus 4, very close to t0 plus 4. The requested message rate is falling from 2 to 1 hertz, and the bottom figure is showing the calculated RPSM is able to be calculated in one step, and it just goes to whatever it should be without any additional cycles of calculation.
Great. So, can I ask a more theoretical question at this point, or is it better to wait for that later?
Of course, sure.
So, thanks for that explanation. So, as you know, Limerick is based on some linear system theory and has provable stability and convergence and fairness properties under certain conditions. Is there anything about the way you're using it with this multiply factor Rmax over Rsys that would have any impact on what normally are those proven characteristics?
I actually went through those how to say it, like analytic proofs that you provided in the weighted Limerick paper, and there was a point that was proven that the proportionality between different rates is translated to proportionality between different betas. And in the thesis, I'm using the same concept. That's the point actually that I'm starting. The point that the paper, weighted Limerick paper, is finished. That's the point that I started in the thesis, and use the concept of time variant and location variant properties of the new environment, and showed that in two equations in the thesis, I showed that different betas are translated to can be translated to proportionality between different rates for various times and various locations. It's not 100% analytical proof, but you know, the equations are I think self-informative. I don't have access to a hard copy to show the committee members what I'm talking about, but it's under section 6 if I'm not wrong.
Okay. So I don't have a firm answer of my own in mind when I ask this question, but as you remember, the limerick stability, there is a bound that's based on the number of participating nodes and the alpha and the beta. And I wonder if when you apply a multiplication factor like you do in step 7 here, if that would have any impact on whether you're above or below the stability bound for a given set of alpha, beta, and K. If in effect now one pedestrian is acting like more than one, for example. So that's something that may be worth considering, whether this would have any, whether this would have any impact on the point at which limerick goes into the nonlinear part of the algorithm that keeps it stable.
Right, that's actually a good point. We didn't do it explicitly in the thesis. What we did through the simulation results, implicitly we are showing that for some of the cases that the calculated RPSM is lower than the requested minimum message rate. And well, by the definition of the algorithm, the controller will prioritize the minimum message rate requested over its own calculated number. We are showing that the system is stable, at least for the case that we have in the simulations. We are not, like I said, explicitly talking about it, but at some level we are showing that for these cases that we have, it is stable. But I don't have the boundaries of when the behavior of limerick is changed.
Okay, that's good for me. Please go ahead.
Okay. All right, and well, like I said, to understand what is the channel load, current channel load, the nodes are not calculating themselves. They transmit, go to sleep, wake up, transmit, go to sleep, right? And that way they are not able to calculate CBP. What they do, we have other nodes out there, secondary radio on the cars, it could be traffic lights, smart traffic lights, who are able to stay awake the whole time, calculate the CBP, and synchronizingly transmit it to the nodes. So nodes only wake up for a proportion of time, just a small amount of time, getting those information from the nodes, knowing what is the CBP, current load of the channel, and rerun the algorithm to readjust the transmission rate, RPSM. Simulation configuration, I'm just putting the numbers here. We defined a few applications here. We try to be reasonable, to stay reasonable in terms of what is the minimum positioning accuracy requested by each of these applications, and what is, what the maximum message rate requested would be. We defined minimum message rate 1/10 of these numbers are max, right? So this is something that we came up. It's not finalized, it's not out there, but we had to have some applications defined to be able to run simulations, right?
So what's waiting for bus? The other one's making sense.
Oh, waiting for bus. So let's say we have a bus station, right?
Okay.
If you are a pedestrian, your phone is transmitting, these messages,
Oh.
and then the what do you call
It's
it?
the
I hate to
pedestrian
do it, say
signaling the car.
smart
Okay.
bus station, but that's
Yeah.
somehow like that, right? Listening to how many messages it's getting and can decide if that's someone waiting for the bus or not. Yep. And one thing that I want to point out here is that we are considering the 10 megahertz channel to be shared with other applications as well, non-pedestrian transmissions, okay? We are considering 50% of the channel is occupied by other applications, right? Because that's what at the time was supposed to be done. The committee that is working on these things was deciding to give this 10 megahertz channel to PSM transmission as well as to other applications. We are considering 50% of sharing here. Okay, so this is...
Somehow that's an ambiguous, ill-defined, so how do you account for that in your simulation? Do you just
Okay. Right.
scale the bandwidth by half, or do you make up synthetic traffic of some sort, and if so, what kind, and does it matter?
It was the first thing that you said, that's right. So the thing is that, we thought about this a lot, how to simulate those non-PSM transmissions. Because at the time, and right now, we don't know what other applications are using that part of the channel, right? We are not able to simulate it accurately. Meaning that, is it something used by secondary radio in the cars for parking matters, right? We don't know it. Because we don't know it, we scaled down the transmission rate. 6 megabit data rate. 6 megabit per second, we actually decrease it to 3 megabit per second. It's not the best way to do it, but given the circumstances, that was one of the options that we could use. Okay, talking about information age. Information age, well, the creators are in this room and in this committee. Roy, John, Marco, I think it started with you, your work?
No, it's Marco,
work?
John, and Sanjay,
okay, yeah.
who invited me to get involved.
Exactly, yeah. I'm very happy. It's an honor to be here. Anyway, everybody these days for safety applications is using like information age. It's a very well-defined metric.
But
And
no one ever calls it information age. You always call it
age of information.
'Cause otherwise,
Yes.
otherwise you get all, you know, Marshall McLuhan citation stuff, right?
That's right. Okay. So remember that I said that some of the key takeouts of the dissertation is redone again with the calibrated simulation, calibrated propagation model. So this is what we have from the same propagation model as the other results were generated with. And rerunning the simulations, everything is the same, remains the same, other than the propagation model, which we use ATC around the corner, longitudinal, the ones that I talked about at the beginning of the talk, right? We are seeing some degradation in the performance, but what we really wanted to show was with different channel models, under different circumstances, you can consider this like a different environment, right? Still, the proposed solution, pet helper meaning that pedestrians' phones are the ones staying up, calculating the CBP, transmitting it to everyone, and then change the roads, right? So pet helper is one of the proposed algorithms that we have. We are showing that pet helper is still outperforming the congestion control from V2V literature. That is the takeaway from this part. And John, remember that you asked me about the one-step calculation of RPSM? Actually, this is what we are showing in these information age plots. The way that weighted limerick was acting, we call it reactive approach, meaning that whenever it gets a new maximum message rate requirement from application layer, it takes it a few steps, a few cycles to converge to the new transmission rate, RPSM, right? But with the proactive approach, meaning that translating different betas to different message rates, keeping a system-wide RPSM, PSM rate, and then calculate whatever it should be in one step, we call it proactive approach. We are showing that the information age could be improved. And two things, yeah.
Ali, thanks for that. I think that's a good point there. That actually leads to a couple of other questions that I had. Do you have a sense of what is an acceptable information age for the pedestrian safety application?
That is a very good question. So I remember we had a lot of discussion with Marco and others. Whenever I got a chance, I was thinking about it. And what we were able to come to eventually was to analyze, whatever that we know, what happens out there. Imagine that one pedestrian is going to cross the street, right? And the few first seconds when they start to cross the street is very critical, because those are the moments most probably drivers are not paying attention that something changed in front of them, right? So based on those kind of like intuitions, thanks for that question actually, because here the information age is showed for the first 3 seconds of walking, a pedestrian walking into the street. So we consider those moments very critical. And if we are talking about a few first seconds of walking on the street, then I think even a sub-second moment for the driver is an advantage. So I can't really put a number on it, but I would say the scale is even less than a second. It can make a difference, especially if we get to a point that the cars are the ones reacting to whatever happening, not the drivers.
So the pedestrians are indicating their position in
Yes.
their message, and kind of what's the noisiness of that position?
It can be very noisy.
Right, but so
When
is
you
it
simulate
1
or-
meter or 2
Right.
or 3
So-
meters?
Yeah, so let me answer your question with this table, table 2. In table 2, we defined a few applications. One of them is VRU in a street, meaning that whenever the phone detects that they are in the street regarding the map and everything, right?
Yeah.
It will transmit. One requirement that the application is asking is sub-meter accuracy, positioning accuracy, meaning that if the estimated amount of error by the device, the API of the phones are giving a number as the estimated error, right?
Yeah.
If the estimated error is sub-meter, this application is enabled. It is transmitting, meaning that the controller is listening to requested message rate by this application. So
Somehow,
that's
okay.
actually one part of the assumption, that we assume that the pedestrian doing this has already a good position for whatever reason. It's either like in a, it has a clear sky view because of the location of the satellites that it gets, right? It
Yeah.
depends to a lot of things.
And somehow I think the answer has to be, right, that to the extent that the positioning system says you're in this circle, right, you should signal often enough so that if you leave that circle, and in essence, if the circle's 1 meter and people walk about 1 meter per second, you ought to have a message every second. You shouldn't have the gauge be more than that, If it's like half a
That's an
second,
argument,
then
yeah.
you're gonna guarantee that, the person is very likely within the 1 meter circle that
Right.
that's within the noise of what the positioning system can provide.
Yeah. That's a good point. But one thing is encouraging us to transmit more than 1 second.
You can average
One
those and get rid
packet
of
one.
the noise, maybe.
That's
Like
one.
if you can get more measurements, then you start thinking about building a trajectory for the person and smoothing it and having more reliable positioning as a result.
That's one. Another thing is that we can't guarantee that every transmitted packet can be received at the receiver. So in case that we have a few consecutive packet loss, it's better to have less inter-packet gap intervals between
Yeah, but that's
transmitted
reflected in the age, right? If you're losing them, right, then the age is exploding, right? So when you say, oh, the age is 1 second, you've already accounted for the lost packets, because the lost packets don't get credit in age.
Right, it's somehow very dependent. These all things that we are talking about, they are very dependent. Yes, but for one part is if we are let's say that the pedestrian, let's make it worse. Let's say that's 1 packet per 5 seconds, right? If that's the case, then if we are going with such low rate, the moment that the pedestrian is walking into a street, we don't know where we are at that interval, right? If we are transmitting more, then there is a higher chance that we update the driver that, okay, the pedestrian is located on this street. Look forward to it, right? So, like I said, a few things that makes it really hard to make that decision to say, okay, 1 second is enough, and we should just go with that. And we shouldn't update the drivers more frequently. This was the, like I said, you're right, these applications, these requirements are not finalized for these applications. It's just what we thought at the moment that is, what makes sense to go ahead with. But getting back to John's question, that's still open question, John. I would say it needs maybe focus of a thesis on what is actually a good information age, or age of information, as Roy's stating it.
Yeah.
But here we are just looking for improving age of information as much as we can.
Yeah. As you're talking about it, I think maybe I'm thinking there might be really two different latency-based metrics. The information age, or the age of information, is more about tracking someone that you're already hearing from, maybe as they cross the street, for example. And if that gap gets too large, then the car no longer has enough confidence about where that pedestrian is to execute an application, a warning to the driver. So that's one thing. But another thing would be if the pedestrian is changing its state from, let's say, VRU nearby to VRU in street, then there's a different latency from the moment that state changes until the vehicle is updated about that. That's perhaps more urgent. So that might be a metric to consider if in the future, if you're looking at that as well.
Mm-hmm. Yeah, good point. Yes, you're right.
I have one quick terminology point. I would not call that the reactive approach, as you labeled it there. As you may know, in ETSI, the congestion control standard has two approaches: the adaptive approach based on limerick, which this is, and something else that's called the reactive approach, which is entirely different, based on a table lookup. So that would probably not be a good label to continue to use for what you're showing here.
You're absolutely right. I take a note to change it. Actually, if you remember, we together we have a paper on it to categorize congestion control algorithms to reactive and adaptive. I didn't want to use adaptive here because, both are using limerick, and limerick is adaptive, but I will look for another terminology here. Sure.
Yep. Good.
Yep, and two cases that, we went through it already, but let me just quickly give you the information in these graphs. I just wanted to show you that whenever the requirements, message rate requirements from the application layer is changed, the algorithm is capturing it with one step. It doesn't need a few cycles to smooth out to the new rate. And that is an advantage most probably when the pedestrian is walking into the street. And case two is when what these figures is showing is that whenever the congestion control is not necessary, meaning that we don't have any congestion on the channel, the algorithm is able to go with the aggregated requested maximum message rate requested. So that's another thing that the algorithm is able to do. And with the energy efficiency feature of the proposed algorithm, which is able to use others' CBP measurement for the sake of running the controller, we are able to decrease the energy consumption by 90%. This is great. This is still theoretical, meaning that we have to use like those all those synchronized message transmissions that are developed for wireless sensor networks. I didn't implement those algorithms directly into the simulations, but it is doable. The literature shows that it is doable, and that's our assumption here. But if we do that, we are able to capture this. And the conclusions, we adopted the weighted rate version of the limerick congestion control and introduced a multi-rate congestion control, which is able to capture time and location variant application requirements. It is designed for instantaneous rate calculation in one cycle, as we mentioned, It prioritizes the application requirements over its own calculated rate. As John said, there is room to show this by math that it can do it with guaranteeing the channel load to be stable. We didn't do it, it's not part of this thesis, but it is implicitly shown by showing the system is working right now, at least for these scenario that we have for the simulation. And the proposed multi-rate channel controller improved age of information. I'll correct that, labels. So, and the proposed controller is compatible with collaborative channel assessment, meaning that other nodes can do the dirty part, the energy consuming part, which is the calculating CVP, and nodes are able to use them. Some related publications to this thesis, and I would like to take this moment to dedicate this work to the passengers of PS-752, the plane crash over Iran. I sympathize with those passengers and their families because many of them were PhD students going abroad thousands of miles away. It's heartbreaking that many of them were PhD students who never see their names in any thesis of their own. So I would like to dedicate this work to them. I want to thank my advisor, Professor Gruteser. Marco, thank you for all those moments that you could have made a decision for me, but instead you chose to teach me something. Let me give you an instance. So we had this disagreement with a collaborator over like something, and for some reasons I wanted to withdraw the paper submission, and instead of Marco making that decision for me, he actually told me how things work, what are the cons and pros of whatever decision that I made. And he actually put it up to me to make the decision, and he said that I will support the decision no matter what. And actually I learned how to do it instead of just go with something that he decides. So thank you a lot for all those moments. Thank you. And I would like to thank John. John, thank you for the first few years we worked together closely. I learned a lot from you as well. Thank you for all those lessons. I would like to thank Professor Yates and Professor Martin for all those discussions and conversations that we had in and out of the context of these theses. Thank you for all of them. And let me thank my former teammate, Bing Cheng. Actually, without Ben, it wasn't possible to do this PhD. I remember all those moments that we were like desperate. We go to each other, to the other one, and ask for help. So how to do it? He was always there for me. And other teammates, Ines and Hongyu, recently we had a lot of collaboration with. And also WinLab engineering team and staff for doing the best they could do to support my work as well as others' work. I would like to thank my family. Well, they probably listening to this talk and having no clue what's going on. They don't know English. But yeah, they made me who I am today. So I can't thank them enough for that. And at last, thanks my friends. You were actually the ones. I had a lot of ups and downs in this country without my family. Thank you very much. It was you that kept me going. Thank you very much for that. And I would like to conclude this thesis. It's been an honor to be a student at WinLab. Thank you.
We have time for more questions. If there are no more questions from the
I'll ask
other.
one. Do you know anything about like civil engineering solutions? You know, I was thinking about your thesis and I was thinking, okay, so when you go to Paris, right, very big intersections, they in fact like put a fence up around the corner and they make you walk around the corner and down 30 yards, and then there's a crosswalk that's not at the corner, it's like offset like 100 feet. Does it help?
I never thought about it, but I'm pretty sure yes, because well, whatever that helps you to manage the crowd and you have some information, additional information about where they could be or where they can't be, or limit the space that they can choose to cross the street, certainly that would help to increase the safety. I'm not sure if we are able to use those information directly into the algorithm that we have here, but certainly it will increase the safety of pedestrians. And I think that's the goal of doing all this, right? So it is important, I think. They can help a lot.
Do you have any conclusions about like, okay, so actually maybe 10 megahertz DSRC is just not good enough for Times Square, or not good, it's not enough capacity for Manhattan?
Based on the observation from the latest simulations that we had, so we had like a few levels of improvements, right? We relaxed some of the assumptions and everything. Based on what we saw at the end, I think age of information of 1 second is good. Like I answered one of John's questions, we are not sure what is the best level of the age of information, but I am sure that whatever makes it better, and we, as much as we can make it better, that is going to give us more. So
Yeah, you didn't really answer my question.
yeah, because I don't really know that answer. So the thing is that we need a concrete analysis on how these things work, translate when we go to the field. Information age of like 2 seconds is how much worse than 1 second in terms of if we really have a pedestrian crossing the street and a car approaching, right? I don't know the answer to those questions. So what we did was making some assumptions, trying to make sense out of it, right? With that, it is good right now. But if there is like a thorough analysis on it, I don't know if it's good or not.
Are people safer traveling in schools like fish? Like somehow when you get to the density of Times Square and people are crossing like a school of fish in a big cloud because of, like, does that make them safer?
The KSI map, the killed and severely injured map of Manhattan in one of the New York City government's documents is saying no.
But is that like normalized by traffic density, pedestrian density?
No, it's actually counting number of fatalities. And I think around Times Square, in the document that I looked it up, it was 3 something killed, and that is apparently not acceptable. It's relative, right? Some parts of the world, I'm pretty sure hundreds is even acceptable. But in New York City, it's not. 3, they want to make it 0, right? Yes.
Are these absolute counts or are they normalized?
Absolute
where-
counts.
So they're not
It was
normalized
per
by the number of
one
pedestrians
fiscal year.
across the
Pedestrians.
Fiscal year, yeah. So most probably it's not good enough.
But it could also be that you're safer there, it's just that a lot more people are crossing at Times Square than
Exactly.
other areas.
Like
Could be
50
translated
times
like
more.
that. Yeah. Yeah, probably the chance of getting hit, because cars can't go beyond like 20 miles per hour, 25 miles per hour most of the time, right?
Yeah, you would have to normal it by number of pedestrians.
Yeah. Yeah, that's probably. But the thing, so I didn't do it because in that document, which is directly on the safety of pedestrians in New York City, right? They are saying that it's not enough. The goal is 0. So I didn't see the point to normalize it, to say that it's really good. We don't need to work it out here.
No, I was just thinking about, the conditional probability you step into an intersection in Times Square that you kill.
With the crowd.
I tend to think is lower than some less densely populated block.
Well, no, there's parts of, like the outer boroughs, like Brooklyn or something, where
I think
there's not many people crossing intersections.
But in some way,
And
that's
the cars are going a lot faster,
that
so you
seems
might
it's
think
a
that would be more dangerous.
Situation. When you think about people
Yeah.
getting killed by the
Yeah.
left turn, they're focused on the oncoming traffic,
Yeah.
and then they don't realize. That's kind of the thing I was, my brain is thinking about.
No, the intersections that are faster are listed.
I mean, anecdotally, I think if I'm driving near Times Square, I don't feel like it's likely I'm gonna kill someone, whereas if I'm driving in an outer borough, I worry about that kind of thing more.
Well, also, I mean, just statistically, somebody else may take the hit,
Right.
You're just not.
Yeah,
You're in a different
you
spot.
would be like, I'll be, you think not defensive.
Pretty sure the mayor doesn't work that
You'll
way.
be
but-
like,
Somebody else.
get in the middle of the crowd,
Yeah.
and someone out, you know, out on the edge will.
This is getting very philosophical now.
Yeah.
All right.
We should move on, okay.
Let's close the session. And does anybody have more questions for Ali in their closed session?
Yeah, I wanna go over some things.
I've got a couple more questions on this and when it's appropriate.
Sounds good.
Actually, close the session.
All right, we're in closed session now. John, why don't you go first?
Okay, great, thanks. Thanks, Ali, for a good presentation. I've got a couple of questions to kind of probe a little bit more on your thinking. The first one has to do with classifying vulnerable road users or potential vulnerable road users. And you spent a lot of time on that, especially on distinguishing between pedestrians that are in different phases on the sidewalk or in the road, stationary, moving. The question I have is about distinguishing